So we've talked about specific manipulations that you can do with series, and we've taken derivatives of series, we've integrated series, we have plugged in variables into series, we've multiplied by variables within a series. But there's another cool manipulation technique that I love and is probably one of my favorite manipulations. And that is where we can turn a rational function into a geometric series. So to build this up, what I basically want to remind you is a couple of things. Number one is that a geometric series happens because we're multiplying by a common ratio. And we've learned also that geometric series are of the form a times r to the n, where a, and I like to use a1 is the first term, and r is the common ratio. So nothing earth-shattering here. So let's say I said, I want you to start with a first term of 2, and I want you to let the common ratio be 3. What would we write as a geometric series? Okay, so let's do that. If the first term is 2, and then I say, okay, common ratio is 3, so 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54, plus so on and so forth. And I could say that this follows the pattern 2 times 3 to the n. And to get that, I'm basically using this format right here to come up with that formula, plus dot, dot, dot. Now we know that this obviously does not converge because the sum is getting bigger and bigger and bigger and bigger. We would also typically refer to this as the n equals 0th term, the n equals 1th term, the n equals 2nd term, and so on and so forth. You get the idea. Now I could alter this by saying, hey, you know what? Let's keep the first term at 2, but now let's make the common ratio -3. Okay, so that would make my series 2. 2 times -3 is -6. Times -3 would be positive 18. Times -3 would be -54. And so on and so forth. And then my formula would then be 2 times -3 to the n. And this would still not converge. But I could do the same thing, and here's where we get kind of fun, with variables. What if I let the first term be 1 this time, and I let the common ratio be x? So that would mean my first term is 1. 1 times x is x. Times x again is x squared. Times x again is x cubed. And this would continue to follow the pattern of x to the n. Now this is geometric. And since this is geometric, I could actually find the sum of this series by taking the first term and 1 minus r. Well, what is the first term? The first term is 1. 1 minus, what's the common ratio? X. And that's a rational function. Now, I think it's important to remember that a series is a sum. This is a sum. This is a formula for a sum. A series is an approximation for a function. So the series is equivalent to this function. So that means we can use our knowledge of geometric series to write power series for a function if we can write them in this formula. Because remember, the sum of an infinite geometric series is the first term over 1 minus r. So we're going to use that to our advantage and do lots of fun stuff with it. So important piece is that it's geometric series written in the form a times r to the n converges to the sum where a is the first term and r is the common ratio. And this only happens if the common ratio is less than 1. We know that. That's the geometric series test. Let's write that. That's the geometric series test. So what will a problem like this look like? All right. I want to find a power series for 1 over 1 minus x squared. So that's our function. F of x is 1 over 1 minus x squared, and I want it centered at 0. Give the first 4 non-zero terms and the general term. Now, guys, I could sit here and I could build a power series for this, but you're going to be here for a while taking derivatives. If you wanted to build like a Taylor series, Maclaurin series, I want to build this using a geometric series. So what if I say, hey, I'm going to force this to be a1 over 1 minus r. So I'm going to force this to be geometric. Let's make this geometric. If this is geometric, that means that the first term is 1. And the common ratio is x squared. Well, okay, I can build a series off of that. If this is geometric, my first term is 1. 1 times x squared is x squared. X squared times x squared is x to the 4th. X to the 4th times x squared is x to the 6th. And I can continue this pattern of x to even powers, which means this is equivalent to this series. So basically what I've just done is I've said, hey, this function is equal to this series. It's just a geometric series. And what do we know about all geometric series? We know that geometric series are going to converge when the absolute value of r is less than 1. Well, what is r? If r is x squared, I need for x squared to be less than 1. Well, how is x squared going to be less than 1? It's going to be less than 1 if x is between -1 and 1. And that is your interval of convergence. Now you're probably wondering, oh no, Miss Lowry, are we going to have to check endpoints? No, I want you to write this note. You do not have to check endpoints or even do the ratio test. Since when the common ratio is 1, geometric series diverge. So I don't need to check when it's equal to. I just need it to be between those two numbers. So what I'm going to ask you to do is go ahead in your graphing calculator. I want you to graph 1 over 1 minus x squared, and then I want you to do the first 5 terms of this series. Okay? So let's do that. Let's go to Desmos, clear this out. Let's graph 1 divided by parentheses 1 minus x squared. So that's going to be my green graph. And then let's go and do 1 plus x squared plus x to the 4th plus x to the 6th. We're going to go 5 terms plus x to the 8th. That's 5 terms. And what do you notice? Let's trace some values here, okay? Now, I can see, here's my green graph. Look where the purple graph ends up on top of it. Here's what's even cooler. Do you know how we said that the interval of convergence was from -1 to 1? Trace some values on this graph with me. Here is -1. Okay. Here is -1. And then as we get in here pretty close, look how close they are within -1 and 1. And I only did 5 terms. If I add more terms to this, look how much closer this is going to get. I'm going to add plus x to the 10th plus x to the 12th. And as I'm adding more terms, it's getting closer and closer between -1 and 1. So what does this mean? So what this is telling me is the series and the function are very close on the interval -1 to 1. But after that, they're very far apart, which means anything outside of that, anything outside of the interval -1 to 1 is not convergent. Not a good approximation. Okay, let's do another one. A little bit spicier. So that one was pretty easy. Let's do another one a little bit spicier. So now we're going to let our function be 12 over 4 plus x. So remember that the goal is to force this to be geometric. Okay, 12 over 4 plus x. Now, if you remember, we want this to look like a1 over 1 minus r. Okay, that's the sum of a geometric series. Remember, sum is the function. We're going to say this function is convergent, and it's going to sum to a1 over 1 minus r. Problem is that this is a 4 right here and not a 1. So how can we do a little bit of manipulation? What if I multiply both the top and the bottom by 1/4 over 1/4? If I do that, what that's going to give me is 3, let's distribute in, over 1 plus x over 4. Okay, so we've got a 1 there, but that still doesn't look like 1 minus r. Okay, let's turn this into 1 minus -x over 4. And now we're cooking with grease, because I can clearly see now that the first term is 3, and the common ratio is going to be -x over 4. So let's build the series. I can now say that 12 over 4 plus x is equivalent to the series first term of 3, 3 times -x over 4 is going to be -3x over 4. Let's multiply by another -x over 4. So that's going to become positive 3x squared over 16. Multiply by another -x over 4, and I get -3x cubed over 64. And what's happening is, because this is geometric, remember that your geometric formula is a times r to the n. So starting at 0, going to infinity. That means my first term is 3, -x over 4 to the n, plus ... So remember, to get your next term, I'm multiplying by -x over 4, by -x over 4, by -x over 4, using that common ratio. So how do I make this thing converge? Well, remember that you need your common ratio to be less than 1. So if my common ratio is -x over 4, let's split this up between -1 and 1. Let's multiply by 4. I'm going to divide by -1. Remember that dividing by -1 is going to flip your signs. So I get 4, flip the sign, -4. But really, that's the same thing as this. And this is your interval of convergence. And you're done. I'd love for you to try this one. It's okay if you don't want to, but I think it's we've done enough that I think you're okay doing this. Okay. Actually, scratch that. Can't do it. I want this thing to be centered at x equals 3. I forgot that. My bad. So my function is 5 over 4 minus x. In the previous two examples, we've been centered at 0. Notice here, centered at 0. Notice here, centered at 0. So now we're going to get a little bit spicier. I want to center at 3. So if I want to center at 3, remember that I need to make an x minus 3 in every term. So every term needs an x minus 3. So how are we going to do that? What I basically want to do is turn this into x minus 3. Well, I can't do that by just subtracting 3. So if I'm going to put an x minus 3 there, in order to balance this out, I technically need to put another minus 3 there. Now, why? Because that's going to give me 0. So essentially what's happening is this is going to shift us right 3, and this is going to balance out to basically make 0. Okay? So I just forced it to have an x minus 3. Combining like terms, we're going to get 5 over 4 minus 3 is 1 minus x minus 3. And now I'm in the format of a1 over 1 minus r. That means that my first term is going to be 5. My common ratio is x minus 3. So let's build a series. That means that my function 5 over 4 minus x can now be approximated by the series. First term 5. I'm going to multiply by x minus 3, so 5x minus 3. I'm going to multiply by another x minus 3, so 5x minus 3 squared. Notice the 5 isn't changing. I'm going to multiply by another x minus 3, so x minus 3 cubed. And this pattern will continue and always yield a 5 and an x minus 3 to the nth power plus dot, dot, dot. And I want this thing to converge, so I need to find its interval of convergence for what values of x does your series converge. So the common ratio must be less than 1. So that means that x minus 3, our common ratio, is less than 1. So we'll sandwich it between -1 and 1. Adding 3 to both sides, we find our interval of convergence. And this is equivalent to the sum of 5x minus 3 to the n. And remember, you are not going to have to check endpoints. Now there is a note that I think is pretty important, so you're going to want to make sure you kind of clue into this. If the center is shifted, the polynomial and series must be also. They have to match. So if I go from a center of 0 to a center of 5, I have to make sure that my polynomial has x minus 5 in every term. So if my center is at x equals c, every term must have an x minus c, which is how I knew that everything was going to have an x minus 3. Now sometimes you might have to do some extra algebra in order to get a specific x minus c to appear. Sort of like the idea behind completing a square. Okay? Now the last thing that I want to kind of go through before we switch gears is I want to show you some different AP style questions that you could see. So speaking on this idea of radius and interval of convergence, these are some AP style questions that have to do with recognizing specific expansions. So here you're going to see a sum and it just says find the sum. Guys, that's code for what is this the series of? What series is this? So if you look at it, let's clue into some things we know. We know that e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot, dot, dot plus x to the n over n factorial. Well, this kind of looks like that. I can see here is 1. I can see some squares. I can see some cubes. I even see this. It looks like x is 3. So if x is 3, that would make e to the third power 1 plus 3 plus 3 squared over 2 factorial plus 3 to the third over 3 factorial and so on and so forth. So guess what? This converges to e to the third power. This is e to the 3. All you're doing is going, oh, I recognize that. So let me test you a little bit further. I look at this next one, looks really scary. Find the sum. Remember, sum is the function. What function is this? What number is being plugged in for x? I can see an immediate clue into odd factorials in the bottom. And that's a pretty good sign because I know that sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on and so forth. So it looks like possibly x is 2. So if x is 2, that would mean that the sine of 2 would have to be 2 minus 2 cubed over 3 factorial plus 2 to the 5th over 5 factorial. And that's exactly what I have here. So this is sine of 2. Okay. Now this last one is by far the hardest one, most difficult one, because it doesn't look like sine and it doesn't look like cosine, but you know what it does look like? It looks like a geometric series. So if this is geometric, and I can see that the first term is 1, and I'm multiplying by a common ratio of negative 2/3, then the sum of this infinite geometric series should be a1 over 1 minus r. So my first term is 1 minus negative 2/3 should be 1 over 5/3 or 3/5. Guys, this is the sum of 3/5. Okay? Another very AP style question. I really like this question. Suppose that the power series, sum of a sub k, x plus 3 to the k, converges if x equals 8 and diverges if x equals 6. Now, what I'd encourage you to do in a situation like this is to draw a number line. Okay? We know that the center is negative 3. How do I know that? You guys see that plus 3? That means it's gone left 3 units. So I'm going to go ahead and start with the idea that the center is negative 3. Now, they didn't tell you what the radius was. They didn't tell you what the interval of convergence is. All you know is this. If I go to 6, I know that it diverges there. If I go to negative 8, it converges there. So I know it has to converge at the center. And if it converges at negative 8, it converges everywhere in between it. So that means that the radius could be 5. So if the radius could be 5, if I go 5 in this direction, that's going to put me at 2. Now, you don't know anything about 2 because remember, endpoints can do different things. But I do know that if it at least converges to 8, then it must converge at least all this stuff in between. And what you don't know is if the radius could be larger because you don't know what's happening at 2. You just know it doesn't converge at 6 and it converges at negative 8. So what's going on in here? I don't know. What's going on in here? I don't know. But here's what we know. I want you to answer the following statements as, is it must be true, cannot be true, or may be true? Explain your reasoning. Could the power series converge at x equals negative 10? Maybe. So where would negative 10 fall? So let's think about this. If the radius is at least 5, the radius could be larger, maybe. The distance from 3 to 6 is 9. If I go 9 in this direction, negative 3 minus 9 is negative 12. It could be that big. So maybe, because the radius could be as big as 5 or more. All we know is it's definitely at least 5. Does the power series converge at 1? Well, that's a must. It must be true. How do I know that? Because if I already know that it converges at -8, it has to be 5 in both directions, no matter what. Could the power series converge at 2? Honestly, maybe. Remember that endpoints can do different things. Endpoints are independent. So just because I know that it converges at -8 doesn't mean it has to converge at 2. Last but not least, does it diverge at -9? Well, not last. I forgot that there's some more on this next page. Does it diverge at -9? Maybe. Notice that's in my zone of question mark. So again, maybe. Well, what about -13? Is it going to diverge at -13? Well, if it diverges at 6, -13 is already out here. It cannot. Or excuse me, it must. It must diverge. Must be true. I was thinking converge. Must be true. Because it's outside of that range. So it's at least 5. It could be as big as 9. We don't know. Does the power series converge at 8? Well, definitely not. Because if it diverges at 6, anything beyond 6 definitely cannot be true. So this is an interesting question because basically what we're saying is the radius could be 5, it could be more than 5, but after we get to that spot of 6, right here, we're not going to be bigger than that. Okay, so a little bit of reasoning. What I'd like to finish out with is a couple of theorems, and these are going to look scarier than they really are, so just go with me on that. Okay, so let's say that we have a function f of x, and we'll say it is some first term, a1 times x minus c, a2 times x minus c squared, a3 times x minus c to the third, plus dot, dot, dot. And I could actually say that this is equivalent to the sum of n equals 0 to infinity, a sub n, x minus c to the n. And what we're going to say is that the radius of convergence of this polynomial is at least center minus some radius and center plus some radius for its interval of convergence. So we're basically saying, hey, here's our center. Let's go plus r in this direction. Let's go minus r in this direction. If I know that f is differentiable and continuous, then the derivative is as follows. I could take the derivative of this thing. So what's the derivative of a0? It's a constant, so 0. What's the derivative of a1 times x minus c? Just a1. What's the derivative of a2 times x minus c squared? 2. a2 x minus c. And I'm just going term by term. 3 a3 x minus c squared. And using my general term, I could even take the derivative of the general term and say it would be the sum from n equals 0 to infinity of n times a sub n x minus c to the n minus 1. While this looks scary, basically all I'm saying is I can take the derivative of a series. And I can even integrate a series. So now going in the opposite direction, let's add a plus c. What's the antiderivative of a0? Well, a0 times x minus c. What's the antiderivative of a x minus c, or excuse me, a1 times x minus c? It's going to be a1 times x minus c squared over 2. And a2 times x minus c cubed over 3 plus dot, dot, dot. And I can say that the series is from n equals 0 to infinity of a sub n x minus c to the n plus 1 over n plus 1. And so essentially, we're saying that I have a radius of convergence of a series obtained by differentiating or integrating a power series is the same of that original power series. Holy cow, that's a big deal. That means if I take a derivative or I take an integral, the radius is going to stay the same. But another big deal is that the interval of convergence may differ because of the behavior of endpoints. So all this big giant text box is saying is I can take derivatives and integrals of power series. That's all it's saying. Okay? So in other words, when you have an interval of convergence of a series, the derivative and the integral of the series will converge for those same values, but you have to check your endpoints because those will not necessarily have the same convergence and divergence. Big idea, always check your endpoints. Now, this is not true if it's geometric. Geometric, remember, we don't care about the endpoints. But if it's not geometric, you have to check the endpoints. Okay? So let's let f of x be 1 over 1 minus x. Write the Maclaurin series for f. Maclaurin means we're centered at 0. So we're going to let f of x be 1 over 1 minus x. Because this is rational, let's treat this as a1 over 1 minus r. So that means my first term is 1, and my common ratio is x. So I can build this series. Let's move this over. I can now say that this is 1 plus x multiplied by another x, x squared, multiplied by another x, x cubed, and so on and so forth, all the way up to x to the n. And because I need this to converge, remember that it's going to converge when your common ratio is less than 1. So we need x to be less than 1. So it's going to converge from -1 to 1. Because this is geometric, I do not have to check the endpoints. Since this is geometric, you do not have to check endpoints. But let's say I now ask you to find the derivative. So use your answer to A to find a Maclaurin series for the derivative. Okay, I'm just going to take the derivative term by term. Derivative of 1 is 0. The derivative of x is 1. Derivative of x squared is 2x. Derivative of x cubed is 3x squared. And this is going to follow the pattern of nx to the n minus 1. Now, we already know that it's going to converge on the interval from -1 to 1. Why? Because if we go back to this theorem that says my interval of convergence is going to preserve everything but the endpoints. So since this is not geometric, I have to check endpoints. How are we going to do that? Well, we have a formula. Look at your formula here. That means that my series is the series from n equals 0 to infinity of n times x to the n minus 1. And so what we're going to do is we're going to plug in our endpoints of -1 and 1. So let's start by letting x equal 1. If I let x equal 1, my series becomes n times 1 to the n minus 1. Well, that's actually not that exciting because basically you are going to have nth term divergence limit as n approaches infinity of n times 1 to the n minus 1. It's just going to keep getting bigger and bigger. And that's not 0. So this thing diverges by the nth term test. We're going to do the same thing with letting x equal -1. So that means I have the sum of n equals 0 to infinity of n times -1 to the n minus 1. Honestly, this is not that exciting either, because if I take the limit as n approaches infinity of n times -1 to the n minus 1, this thing is also going to keep getting bigger and not equal 0, and is also going to diverge by the nth term test. So both of these endpoints end up not included, which is fine. Now, another possible follow-up question, and I love this, it says use your answer to B to find the sum of this infinite series. And this is where things get super tricky. Use your answer to B. Guys, they want this to somehow connect to your answer to B. So what I would do is I would start by stacking your answer to B. 0 plus 1 plus 2x plus 3x squared plus ... nx to the n minus 1 plus ... Okay? They want you to use your answer. And remember, this is equivalent to the derivative of the original function. So let's make some connections. Here I see 1. Okay. If I look at the next term, this is 2x and this is 2/3. If I look at the next term, this is 3x squared and 3/9. If I look at the next term, it's going to be 4x cubed. And so I can make a conclusion that it looks like x is possibly 1/3. So if x is 1/3, then the sum of this infinite series should be the sum of its derivative. So check it out. If I plug in f prime of 1/3, I get 1 plus 2/3 plus 3 times 1/3 squared plus ... n 1/3 to the n minus 1 plus ... So let's rewind. If f of x is equivalent to 1 over 1 minus x, which I could rewrite as 1 minus x to the -1 power, the derivative, if I actually took the derivative of this function, it would be -1, 1 minus x to the -2 times -1, because of chain rule, which is really 1 over 1 minus x squared. So if this function right here, f prime of x, and this series right here are equivalent to each other, remember, they're the same, then can't I just say that this is equal to 1 over 1 minus 1/3 squared, or I am plugging in 1/3 for x? And I can. And we know that 1 minus 1/3 is 2/3, and 2/3 squared is 4/9. This thing has a sum of 9/4. What in the heck did we just do? Well, we figured out what x was. We took the derivative and we plugged in x equals 1/3. That's all we did. Okay. So I'd like to take you through another kind of free responsey sort of example. And the examples that I'm going through, these are actually really, really similar to the ones that you're going to see on the real AP test with regards to series. So these are actually adapted and modeled from real AP exams. So now I'm going to change f of x on you. We're going to let f of x be 1 over 1 minus x. Actually, I lied. That's the same f of x. Sorry, guys. And let's let that be geometric again. So much so that I can say that the first term is 1 and the common ratio is x, just like we did before. So we're going to start by just writing the Maclaurin series. 1 over 1 minus x is now equivalent to 1 times x times x times x, so on and so forth, x to the n. And this is actually good for negative 1 to 1, because remember that the common ratio must be less than 1, so therefore that means x is between negative 1 to 1. Okay, so this is our interval of convergence. So part 2b, we want you to use your answer to A to find the Maclaurin series for this. What are they asking you to do? Well, if this is f of x, then f of t is this same function with just t's plugged into it. So if I want the integral from 0 to x of f of t, I need to take this function right here, and I need to plug t's into it. So 1 plus t squared plus t cubed plus dot, 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 t to the n dt. Well, I can take the integral of that. That's easy. Go term by term. Let's integrate. Integral of 1 is just going to be t. Make sure you're using the right variables. T squared over 2, t cubed over 3, t to the 4th over 4, so on and so forth. Let's actually do the general term. T to the n plus 1 over n plus 1, dot, 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 evaluated from 0 to x. Well, that's just code for plug in x, plug in 0. 0 is going to give me all zeros. So let's go x squared over 2, x cubed over 3, x to the 4th over 4. It does ask for the first 4 non-zero terms. Check 1, 2, 3, 4, and the general term. So x to the n plus 1 over n plus 1. Done. Notice it says, for what values of x does it converge? Ah, dang. Well, we already know it has to be good from negative 1 to 1, but this is not geometric. And if this is not geometric, we need to check endpoints. So we're going to do that. Remember that this is your formula right here. It is the series from n equals 0 to infinity of x to the n plus 1 over n plus 1. So let's start by letting x equal 1. I tend to start with the positive one. I think it is a little bit easier. So we're going to say 1 to the n plus 1 over n plus 1. Well, that's not that exciting. If I compare this to the series 1 over n, which we know diverges, and if I do limit comparison, and I know I don't have a ton of room, but I'm going to squeeze it in here. Let's do limit comparison. I'm going to take the limit as n approaches infinity. Remember that it is original series over the comparison series, multiplying by the reciprocal. We get 1. 1 is positive and finite, which means it's going to diverge, behave the same, by limit comparison. Okay, well that's just x equals 1. What the heck? Let's do the rest. Okay, so I need to also let x equal negative 1. I'm going to change colors for that and kind of squeeze over here. This one is not as spicy. N equals 0 to infinity. Now we have negative 1 to the n plus 1 over n plus 1. This is going to be an alternating series, I can tell that. So let's go number 1. Does it alternate? Check. Is this thing going to decrease in magnitude? Sure is. And if I take the limit as n approaches infinity of 1 over n plus 1, you do in fact get 0. So this thing is going to converge by the alternating series test. So what does that mean? If I go back up to my original answer, I need to throw an equal sign on -1, but keep 1 without it. For the last question that says use your answer to be, guys, when they tell you use your answer to be, they really want you to make sure you're making some connection there to find the sum of this series. Well, let's look at our answer from part B. In part B, it was x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 plus ... x to the n plus 1 over n plus 1. Okay, so that was our original. It looks like x is 1/3. Well, remember what this is equal to. This thing was equal to the integral from 0 to x of f of t dt. So if x is equal to 1/3, I probably should use a different highlighter color. There we go. X is equal to 1/3. That means I need to plug in x right there. So the integral from 0 to 1/3 of f of t dt is now equivalent to the sum 1/3, 1 over 3 squared times 2, 1 over 3 to the 3rd times 3, 1 over 3 to the 4th times 4, plus ... 1/3 to the n plus 1 over n plus 1. Okay, well, what is f of t? What actually is f of t? Well, let's do that. Integral from 0 to 1/3. Go back up to the original. Notice f of x is 1 over 1 minus x. So let's substitute in 1 over 1 minus, instead of x, let's put a t there, dt. Can I take that antiderivative? Yeah, I can. If I make u 1 minus t, that means du is negative dt. So this thing is going to become the integral from, let's change our bounds. Let's do that too. The integral, if I plug in 0, 1 minus 0 is 1. Plug in 1/3. 1 minus 1/3 is 2/3 of 1 over u, du, with a negative on it. What is the antiderivative of 1 over u? Natural log absolute value of u, and it's going to be negative. We're evaluating that from 1 to 2/3. Let's plug it in. Negative natural log 2/3 minus negative natural log of 1. We know that the natural log of 1 is 0. So this is the negative natural log of 2/3. If I put this negative exponent right here back, this is really the same thing as the natural log of 2/3 to the -1 power, which is the natural log of 3/2. Guys, this is the sum of that series. It's just the series evaluated at that value, okay? So that's where I'm going to take you for today.